Yeah, in the group velocity, we got part of it. That's the derivation of uh, uncertainty principle, which is, I mean, not needed, but it's just good to know that because this is fundamental. It's not just for E and M, it's for, I mean, it's more fundamental even quantum mechanics. So good to know the physics. And then for us, the application of the uncertain principle is that for our situation, we can use that to argue that delta k is very small because we are considering a propagation of something that close to a plane wave. Plane wave is infinitely long, but this is not infinitely long, and then it's just of a single wavelength, a single wave number. It's like a sinusoidal wave, but it's spread off after a long distance. And like you have um, profile or envelope, right? And because this delta x is long, this distance long, then this is in the physical space x, so this is u is x, right? And then later on we consider how you change it in time also. And then obviously, because delta x is large, then you can allow a small delta k. There's an inequality, so delta k can also be large, but it's allowed to take a small value. So then this k in the k space, then you have a pulse, very narrow delta k, and with a k or whatever you call it, k sub 0, that is corresponding to the wave number. Wave quasi plane wave. It's like a single frequency wave, but then it's just fall off over a large distance. And we're using that because for talking about the group velocity, we want to do a Taylor expansion. Okay, so what we do is we write down this U in our situation, how it evolves in time. Basically, it's a Fourier transform that last time we talked about this. Fourier transform in space, so it's decay. So you have some kind of a which is determined by the initial condition when t is 0. Then we can do a calculate the Fourier transform a at t goes 0 because you just multiply by e to the minus ikx and integrate over x, and you get this a sub k. Right? Just use the formula. Now for the expression in x and t for later t, so first you have this Fourier transform, and then you have the ikx term. Right? That's this part of the Fourier transform, but then hk is supposed to be moving in the frequency. So it's minus I omega t, but the omega now depends on k, right? Assuming that we have a medium that this omega is not just depends on k, it depends on k. It's non-linearly depends on k. Otherwise, because we already know that ck omega is n. I didn't mention. If n is just a constant, then omega is linearly proportional to k. That is non-dispersive medium, right? And then the group velocity will be the same as the phase velocity, but allowing that, in the general case, it can depends on k in the nonlinear and times t. Okay, so if it is constant, if it is linear, then we see that from the formula, the group velocity is the same as the phase velocity. Okay, so now because of this assumption that the k is small, then you do a Taylor expansion. So omega will be we'll take and omega will change to evaluate that as the original, almost like the single frequency rate, so case of zero. And then the next term will be dk evaluate at the case of zero, and then k minus case of zero. All right, and then there could be other higher order terms. But for the discussion of group velocity, we just keep to this linear term. The second order term will be needed, or at least the physics is needed in the next section. Talk about the envelope actually change also, change slowly and broadening. So that's why we call it dispersive. The wave is kind of dispersing. Okay. Okay, so now we have you want to regroup the argument of the exponential function. First, you have this term has a k, this term also has a k, so that will allow you to group it together. To the ik. Now we group these two with the both have ik. And the first term has an x. The second term has a minus sign, so minus d omega dk. Evaluate case of 0 times t. Right. And then the rest are constant. I mean, at least not depends on k. This is evaluate at case of 0. This is evaluate case of 0. This is case of 0, and it only depends on t. So everything is proportional. So this is like a phase. Minus omega case of 0. Evaluate case of 0 times t. So this is a purely phase in time. Okay, it just shifted the frequency by a little bit. Okay, and this one is out of the integral. There's no k here. So everything else here is exponential. This is just a phase out of the integral. So now you can just consider this part as your integral. And now you compare with the original profile. So basically, you originally you set t equals 0, right? And then when t goes 0, you get rid of that. Right? So that would give you this equation. So you compare this one with this one, this integral. You see that they are exactly of the same form, exactly the same form. The only thing you need to change is, so this is kx, this is k times this factor. This is x minus this d omega dk times t, and d omega dk has the dimensional velocity, and we can give it a name. So give it a name, v sub g. So therefore, this is just u x minus v sub g times t, and multiplied by a phase, whatever that is. Basically, it's the original frequency shifted by a little bit. But this is just phase. It's purely sinusoidal because it's e to the I of this. This is purely real. All right. So this factor x minus v sub gt is just that at the later time means that the whole envelope move. This is u. Say assuming this is at t equals 0, and at t equals to a finite value, the whole distance shifted by this Vg times t. This is Vg times t. So basically, the envelope now, original envelope is here. The later envelope is something here, right? Something here. And then is still the same Fourier transform with the same k, so it's oscillatory. It's also oscillated in time with this one, but this is just how the spatial pattern changes in time. But the spatial pattern in space is given by exactly the same Fourier transform. So like a whole thing just move in this velocity sub gt. Yeah, it's the whole envelope moving in this velocity. So therefore, this is called a group velocity because the whole thing as a group is moving. So you can just write it down and look at it in a little bit more. So it's dk, d omega over dk, when you express omega as a function of k, and then evaluate at a certain k, but just for definition, for a given k, just take the derivative of omega as a function of k with k, with respect to k, and then that is your phase velocity, a group velocity, and that's different from the phase velocity. So phase velocity is omega over k, and from this, you know that this is c over n. Right? And obviously, if n is a constant, then the omega is c over n times k, and the omega of dk is just the same as just the same factor c over n, same as v sub p. So it will not be different with v sub p unless n is also depends on frequency or wave number. I think Jackson has another formula. Let's say the n is a function of omega. I mean, this is taking a derivative of with respect to k, but you can also change it to derivative over omega anyway. So this is just they are all related together. Like you can work that out what Jackson means. You know what I'm saying? Um, so basically, this is 7.87, but you can also divide 7.88 and no. this is 7.88. This is you can divide 7.88, which is I mean straightforward taking derivative. You can do that. So basically, if omega is c times k over n, right? When you do that, you can use the property of the taking derivative that this is 1 over dk derivative. Right. The omega dk is just 1 over dk derivative. You know that way. So and you can now change k as a function of omega as n times omega divided by c. Right? You take the derivative. 1 over the derivative d omega. So the first term is n over c. Just take the derivative over omega is n over c. The other is plus n over c. Omega over c dn dn. That would be 7.89. I mean, after you put the c in the numerator, it's the same. Okay, so that's straightforward. So there's more than one way to calculate. Depends on which one is more convenient to express omega is a function of k is easier, we can calculate it this way. But if n as a function of omega is easier, then we can use this formula. More it's straightforward theory. Is that okay? Any question about this?